What can we learn about a 37-year-old game from interviews, reverse engineering, larger-than-life visualizations, and a trip to a medical center? I'm John Aycock. Let me tell you an epic research story 7 years in the making. This is a story involving the TI-99 4A home computer, which was released in 1981 by Texas Instruments and had a few years of sales before TI announced their exit from the home computer market in late 1983. The celebrity TI found to pitch their computer was none other than Bill Cosby. I see no possible way this could have gone wrong. In 2013, 30 years later, I was starting to do the research that would eventually culminate in this book in 2016. I contacted Scott Adams to ask him some questions. He's a famed early computer game entrepreneur and one of the people behind the now defunct game company, Adventure International. This is Scott Adams circa 1984, shown here sporting a legendary amount of hair. As I was Googling Scott, which sounds naughtier than it is, I stumbled across this quote attributed to him regarding the TI-99 4A game Return to Pirate's Isle. This cartridge-based game was published by Texas Instruments in 1983. A slightly older Scott kindly confirmed for me in 2013 that the quote was accurate, but he couldn't recall any of the implementation details of the game. Here's what the game looked like, an illustrated text adventure game. In particular, if you look closely at the fuzzy picture Scott mentioned, where in the game you aren't wearing your glasses yet, the blocky nature suggests that these might be graphical tiles of some kind. This was exactly the sort of example I wanted for my research. I wanted to figure out how the graphics in the game were created, but the source code used to create the game was probably long lost. However, this isn't necessarily a show-stopping problem. The process of developing these games worked like this. The programmer would write the game's source code in assembly language or some high-level language, and it would get translated by a compiler or an assembler into the binary code that the computer could understand. For Return to Pirate's Isle, all we're left with is the binary code. Enter reverse engineering, which is the process of going backwards from the binary code and figuring out how it works, effectively reconstructing the knowledge that would have been in the original source code. In other words, I could figure out how the game's graphics worked, starting only with the binary code. Reverse engineering is something that, as a computer scientist, is within my skill set and that I have experience with. I mean, really, how hard could it be to reverse engineer this game? It did not go well. For reasons I'll talk about later, it made more sense to abandon the approach of understanding the code and focus on understanding the data directly. I treated the code basically as a black box and didn't bother trying to figure it out. If you wonder what this process looks like, I saved my notes. For me, it started like this and went on for a little while. And that was followed by this, and we can't forget these. In the end, success. What you're seeing is not a game screenshot. This is a reconstruction made by a program I wrote that used data directly from the game cartridge image. It might seem funny to write code to understand code, but the reconstruction is effectively a demonstration, a confirmation that I got the reverse engineering correct. Notice the caricature of Scott Adams and his fabulous hair. I followed up with Scott in 2014 after I finished, and had the somewhat surreal experience of explaining to him how his own code worked. So in the end, I did answer the question about the game's graphics I had, but I'd be lying if I said that failing to reverse engineer the code itself didn't bug me. Around that same time, I was looking at another TI-99 4A game called Parsec. It was doing some clever juggling of graphics in the computer's graphics memory. The problem is, unlike some other contemporary computers like the Apple II, the TI-99 4A didn't store its graphics in the computer's main memory. It had a separate area of memory for graphics that couldn't be viewed easily. What I needed to be able to do was to see what was going on in that graphics memory. So I gathered a large data trace for Parsec as it was running in the emulator and created a visualization program that would allow me to see the entire contents of the graphics memory as the game ran through the data trace. You can see here what my visualization looks like compared to an actual gameplay video. The graphics memory data are being shown in detail along the bottom half. This is running on our university library's visualization studio, which is a massive wall of screens. For scale, you can see the keyboard and mouse here. It's massive and lets me see all the graphics memory data all at once. Because I noticed that Return to Pirate's Isle used the same graphics mode as Parsec, I could grab a data trace from Scott Adams' game and see it in the visualization too. And I noticed a weird pattern. I apologize because I'd originally intended on going back into the visualization studio and capturing some video footage for this talk, but pandemic. So instead, you get to see it running on my computer monitor. Luckily, I developed the visualization using my much smaller computer screen before taking it to the Viz Studio, so it does run okay here. What you're seeing at the top is what would be shown in the TI-9940's video output. Here's the TI logo at the start of the game, for instance, and the bottom half is showing a portion of the graphics memory contents. Okay, now I'm shifting the lower viewport so we can see the graphics memory patterns a bit better. And as the game's data trace runs, recreating the graphics memory accesses the game made, you'll see on this fourth row of graphics memory blocks that there's a distinctive access pattern, sliding back and forth from left to right and right to left, but not really jumping around randomly at all. You can also see graphics memory activity that correlates directly to the text as it scrolls on the screen. This activity is expected. It's really the back and forth memory activity that caught my eye. Specifically, what it reminded me of is a data structure used by computers called a stack. A stack can be thought of as, well, a stack of plates, if you like. When new things get added or pushed onto the stack, they get added to the top. And when things are removed from the stack or popped, they're also removed from the top. So really, any stack activity would be strictly at its top always, which is why that back and forth activity I saw in the graphics memory visualization made me think of one. Which is an interesting observation, but since it related to the code, and I'd already figured out what was happening with the graphics in Return to Pirate's Isle, I never followed up on it. But later, in 2016, I stumbled across this interview snippet by accident, although there was no context. Nothing the person mentioned connected this statement to a specific game. Why was the mention of the fourth language thought-provoking? Well, fourth has an interesting computational model that the programmer uses, and one of its distinctive features is that it heavily uses not just one, but two stacks. Could Return to Pirate's Isle be written in fourth, and its interpreted fourth code being what I found so inscrutable to reverse engineer? For lack of regular memory, one of its stacks could have been located in the graphics memory. A tantalizing hypothesis that I would need to immediately follow up on 3 years later. I mean, sometimes other things get in the way of revisiting what was, in some sense, an already solved problem. When I did get back to Adam's game at last, I started by locating known fourth implementations for the TI-9940 to see if any of them would match what I was seeing in the Return to Pirate's Isle code. Wyco fourth was right out, it required too much memory. TI fourth did have some points of similarity, but that may simply be chalked up to the fact that the TI-9940 was a fairly constrained computer, and there are a limited number of ways to do some things. Either way, neither seemed like a smoking gun. It might help to explain at this point why the game's code was so hard to analyze in the first place, and to do that, we're going to need to talk about registers. A register is a very high-speed location in a computer's CPU where a value can be stored and used. The CPU's instruction set allows a programmer to refer to those registers either explicitly or implicitly. Basically, this is the CPU's prime real estate. As a simple example, the omnipresent 6502 CPU from that era has 6 registers, or depending on your point of view, 1 useful register and 5 others that hang out with it. What about the CPU in the TI-9940? Here's a small excerpt from the Return to Pirate's Isle code. This is assembly code for the Texas Instruments TMS 9900, which is the CPU inside the TI-9940. It was a 16-bit CPU, which is already highly unusual and luxurious for home computers of that era. In fact, the TI-9940 that preceded the 4A was the first ever 16-bit home computer. And it would appear that the CPU has many, many registers looking at the instructions. These registers starting with the letter R are referring to registers. And there are so many different ones. R1, R2, R5, R12, R13. Wow! It turns out this is a cruel hoax.
Fake news.
You see, these 16 quote-unquote registers were located not in the CPU, but in the computer's main memory. The CPU itself had a register called a workspace pointer that would identify location in main memory where the 16 registers were located. What that means is that when trying to understand the assembly code, everything you think you know about the contents of those registers can change in a split second. To make matters worse, the CPU allowed, nay, encouraged use of instructions that could cause the program to jump any place. Where the location the code would jump to is contained in a register. Remember those registers that are tricky to keep track of the values of? These are features of the regular TI-99/4A, and amazingly enough, that wasn't the really annoying part. To make matters worse, the code for Return to Pirate's Isle was storing addresses in the video memory, that memory that was hard to look at before, and would read an address from the video memory and use that as an address to go to in the main memory. That was really the straw that broke the camel's back. If all this sounds very confusing, that's kind of the point. What I was just showing you was a static view of the code where you try to analyze the code when it wasn't running. However, some things are easier to see when reverse engineering if you have a dynamic view of the code when the code is running. We can have the emulator capture this dynamic data in an execution trace, which you're seeing the beginning and end of here. This is showing us the exact sequence of instructions that the game ran and the order it did it in. This information solves a number of the problems that I was having analyzing the game before, except for one slight complication. It's huge. Now, while I could have tried to stubbornly grind through this, it occurred to me that humans are really good at spotting patterns, and it'd make more sense to build a tool that would visualize these execution traces in some meaningful way that allow me to reason about the code. In a technical sense, effectively what I could do would be to graph the dynamic control flow that was captured in this execution trace. What does that look like? Here's an early version, once again running in the Visualization Studio. This early version was less than revealing. The problem, as you can just make out in this picture, is that the graph that got drawn was very dense and looked like a hairball that a cat horked up. But the data this graph is based on is a sequence of instructions. There's a chronology to it. To simplify the graph, I could break up the data into strata. This data corresponds to the start of the game where there's various keyboard input. Y or N for printer output, Y or N for reloading an old game, then hitting keys to page through the game's opening credit text. Because each of those keyboard inputs is implemented as a call to the TI-99/4A's ROM, I used that as a signal that a new epoch was beginning. The new graph is still complicated in some places, but it's clearly in some smaller discrete chunks now, 8 of them, which gives a good starting point to begin understanding the data. Let's have a look at the interface for this visualization. It's actually running in browser. Each of these graph nodes corresponds to one or more instructions in the data trace. We can hover over nodes and labels. Here it's letting us know that the code in this node is repeated 35 times. We can step forwards and backwards in the trace, and of course you've noticed that I can attach virtual sticky notes to document what I figured out about the code. I can search the graph to find all the places where a particular address appears, and look around in the graph and jump back to where I was before. My favorite effect is this diffusion, which let me get a sense of what graph nodes are involved following this point, which is helpful when the graph edges get a little complicated. What did I find out using this visualization tool I built? I'll come back to that in a moment, but first. In between 2016 and 2019, I had acquired a physical copy of the Return to Pirate's Isle cartridge off eBay. I was curious, what's inside the cartridge exactly? Here's the back side of the cartridge, home computer command module. A bit of a throwback to the heady days of the space race happening at Texas Instruments, but then Texas is home to NASA's Mission Control, so perhaps that's not surprising. How would we take this cartridge apart? Unlike an Atari 2600 cartridge, which I know is held together by a screw, this cartridge seems to be held together exclusively by plastic, and in particular this one piece of plastic that I'll refer to using its technical name, the breaky bit. There would appear to be no non-destructive way to take this apart and see inside. I realize that research involving destructive processes isn't unusual in archaeology, but as a computer scientist, and more importantly, the owner of this cartridge, I found the notion somewhat annoying. Is there some way to get around this problem? I realize that I work at a university that has a medical school, and somewhere, there must be an X-ray machine I can use. A few inquiries later, and I'd found one. Sharp-eyed viewers will notice that this isn't the Return to Pirates Isle cartridge. This is an Atari 2600 cartridge I used as a baseline image, one that I don't care about and that I've taken apart before, so I could compare the X-ray images with the reality inside the plastic case. Here's the Return to Pirates Isle undergoing its diagnostic procedure. And if you've ever wondered what dosage you should irradiate your game cartridges with, the answer is medium adult. Here's the baseline Atari 2600 cartridge images, both top and side views. Some things, like the screw holding the cartridge together, are readily apparent. Here it is after they did their usual X-ray image processing, and there's a couple of things to point out. First, the ROM chip inside the cartridge has a metal RF shield around it, and I wasn't sure how this would come out on the X-ray. As it happened, the X-rays went right through it, but you can see a clear outline of it in the image. And speaking of the ROM chip, we're seeing right through the ROM chip's outer packaging. You can see the chip's die inside and the connections between the die's pads and the IC's pins. Here's a comparison between the X-ray image and the actual innards of the cartridge, both with and without this RF shielding. The traces on the printed circuit board actually show up better in the X-ray, which is effectively showing us the traces on both sides of the boards at once. And now for the main event, the Return to Pirates Isle cartridge. At first glance, there's quite a lot of stuff in here compared to the 2600 cartridge. It doesn't look like any RF shielding is present, and knowing the pinout on the cart, we could actually start tracing some of the circuitry. There's a legible label here that must be etched into the printed circuit board. Based on the number of pins this chip has and the baseline 2600 cartridge, we might expect that this is the game's ROM chip. But then, what are these 5 smaller chips down here? Support logic? That seems like quite a lot. We also see visible wrinkling of the traces on the printed circuit board. These are electronic components. Unfortunately, the 2600 image didn't have any discrete components like this, so we have nothing to compare against. In the end, there were too many mysteries, and I had to open up the cartridge to see what was showing up in the X-rays. I want to pause to allow you time to appreciate this image, because opening the cartridge wasn't easy, and blood was spilled, literally. My intuition was correct. Opening the cartridge damaged it, most notably the breaky bit I identified earlier. It's interesting what wasn't showing up well in the X-ray, and here there's a big capacitor that was barely visible in the X-ray image. As for where the chips are, the labeling doesn't give too much away, but we can trace the lines from the edge of the cartridge to make an educated guess. That would have been possible in the X-ray, but it's obviously a lot easier now. Here's the back side of the board with a label and the wrinkled traces. This brings us to the end of this tangent, brought to you by
A scientist whose motives are entirely dedicated to evil.
Now, what did I learn from studying Return to Pirates Isle's execution trace in my visualization tool? On New Year's Day 2020, I had an epiphany. It finally dawned on me that I could just be overthinking it. The weird access patterns and the behaviors I saw in the code execution could be explained by a regular stack if one were implemented, via Scott Adams' code, in the TI-9940's graphics memory. There are really 4 stack operations I was seeing. Saving a return address by pushing it onto the stack, returning to an address by popping it off the stack, saving and restoring register values by pushing and popping them respectively. I wrote a program to run through the long data trace and verify that it was in fact being accessed appropriately in stack-like fashion. Why keep the stack in graphics memory? An unexpanded TI-99/4A had only 256 bytes of RAM, meaning the main memory that, among other things, the CPU's fake registers needed to be stored in. If your program is using code that was in the computer's ROM, then even less of that 256 bytes would be available to you. On the other hand, the graphics memory was comparatively capacious at 16K, 64 times larger than the main RAM allotment. Especially for a text adventure game that didn't need to run especially quickly, keeping a stack of information in the graphics memory would just make good sense. Mystery solved. And this is a screenshot. Thank you very much.